And welcome. My name is Andreas Fertig, and I work as independent trainer, consultant, and occasional speaker. And I'm also the creator of C++ Insights, which is the topic of the talk today. So I'm really happy to talk about the program. Before we dive into the program or C++, let me tell you a short story about my name. I'm doing this for quite a while now. My last name is Fertig. And in German, that's an adjective. In English, it can be translated to finish, or completed, for example. There is also, I'm made aware about that at NDC Oslo, there is a Norwegian spelling for it, which is pronounced Fertig. So I learned that. I now also know that Bjarne Strostrup is at least able to read German because he understood that my last name means finish. In German, the adjective is spelled with a lower first letter because it's an adjective. If I type my name, it starts with a capital F. So I constantly fight with the spell checker whether I'm right or the spell checker is right. It's a fight I cannot win. So anyway, it's hard for the spell checker. We are here today because of C++. And this piece of code should be the motivation or one motivation for why I created C++ Insights. These are two lines of code. I have something here called myType. I create an object out of it called I. Do praise default initialization, and then I post increment I. Post incrementing is maybe not as efficient as pre-incrementing. And when I'm teaching, I try to encourage people to use pre-increment as often as they can and post-increment only if it's really needed. And then they ask questions, especially if I'm lecturing, what's the difference and why? Just from this example, you cannot tell, because myType can either be an alias to an int or some other built-in trivial type. Then it makes no real difference whether you do a post or pre-increment. MyType can also be a class type, which implements operator ++. And then it makes a difference, because in that operator, I have to create a temporary, and I have to create a deep copy of that object before. If it's holding a large or huge std string, it costs me memory, it costs me time. So it makes a difference. But I cannot tell. And then students ask me, where? I cannot see it. And then I say, okay, look at this. It's I.operator ++ in parent 0. 0 is because it's the post increment. The B increment comes without a parameter. That's the only difference. So if I can show things to people, I, at least myself, can teach it a little better, and in my experience, they understand it a little better. Another example is this program. Short program, it implements a max function that returns the creator value of either A or B, and then prints that out with a printf. Question number 1. What is the output of this program? Guesses? 1. Exactly. 1 is the output of this program, because we are looking at integer promotion and implicit casts. We cannot see them. We use them often in C++. They are not necessarily bad, in my opinion, but we cannot see them. This is the website of C++ Insights. You can use it either at a website, or you can install it locally and run it as a Linux or Mac command. And I have here the example from the slide. And if I now transform it, then we can see, oh, the code the compiler sees or uses is slightly different. There are implicit casts. If you look at a max function, then we first can see A and B are promoted to assigned int. because there is no comparison of two shorts. Int is the smallest type that's comparable, so it will be promoted to an int. But that's not the part which bites us here. There's another integer promotion. The return value of max, which is also short, is also promoted to an int when it's passed to printf. And then I have here another static cast, casting my unsigned short, which is a huge short before, into a signed short. It makes it a -1, and that's why 1 in this case is greater than 65K. It makes it easier for me to explain things if I can show them. If I not just have to use words, I can show it. I can show what's changing if I remove, for example, this unsigned here. First I get now a compiler warning, and the cast here is gone away. Of course, there's no reason to cast it anymore. So these are 1 or 2 reasons why I created C++ Insights. The idea here is that the tool should show what is going on under the hood, what lovely things the compiler does for us just to make it easier for us to write code, because the implicit casts I showed you earlier, they're not bad necessarily. In that example, they bit us, but in other places, they spare us typing. So in general, they are good. But making invisible things visible can help when teaching. The other goal is C++ Insights should generate valid code, if possible. And that's for 2 reasons. One, I can test valid code. So I can verify that the output at least compiles. That's not total garbage. There are still possibilities that it does not do the right thing, but at least it compiles. The second thing is imaginary code is nice, but I have a really huge imagination, and it doesn't help anybody. I should write sci-fi novels, but if I come up with something very made up in C++, that wouldn't help. So that's why to create valid code out of it. It means also to create, of course, code that compiles. The program itself, it's open source. You can fork it or submit GitHub pull requests, and you've already seen the website. While we are here, I think it's also worth to talk a little bit about limitations of the program, because if you're using it, you, I think, shall know about it. C++ Insights uses the nice and lovely infrastructure of Clang. It's a Clang tool that has the nice side effect that I do not need to parse C++ code myself, which is, of course, a trivial task, but it was nice that I didn't have to learn. That's not so trivial at all. That also implies that everything it shows is how Clang does things. GCC might do things a little different. There is room in the standard for interpretation. There can be provide both a valid implementation, but it may differ a little. If you're using the release version, either on the website or the command line tool, then this compiles under Linux against libstd.c++, while the Mac version compiles against libc++. Looking at certain things of the standard library, you will see differences there. For example, how they implemented std_string or things like that. So this will look slightly different. Still works and so on, but it's worth noting. The release version as well as the web version are based on Clang stable, the latest Clang stable version available. That's to have a stable code base to compile C++ Insights again and to make issue reporting and resolving issues easier. The source itself I try to maintain in a way that it's up to date with Clang current, so I already have patches to enable Clang 9 support, which will bring us some of the C++ 20 features for Lambdas, for example. Clang 9 is a little bit behind schedule right now. It was supposed to be released in end of August, but I think we will have it in a couple of days or so. What C++ Insights does is it uses the Clang AST, so the already processed C++ program, the abstract syntax tree Clang generates, and transforms that back into C++ code. As this AST is generated at an early stage in the front end, you will not see any effects of optimization. So it doesn't make a difference whether you're passing -0 or -03 to the program, because most of these optimizations happen afterwards. You will, however, see simple things, or in some cases, a constant expert evaluation, if it's possible in an early stage. Other simple things, trivial things like building the sum of 3 plus 4 is something the front end does while walking through the code, basically. So these are the things. When talking about limitations, there is something big in C++ which creates some hard things, and that's templates. You will see also template instantiations in C++ Insights. So you get a better glimpse on what types or what instantiation of a function are instantiated in the compiler. That does not necessarily mean that all of them survive until the end of the compile stage, so linkers and optimizers are able to throw things away, but they are created at some point. In my experience, Clang is so smart that it does not bother to create template instantiations for types that are not used. So that's a nice effect you can see there, which type is used or which type is not used. And what templates bringing, which makes it hard to generate correct code here. If you look at this example, I have here this function template called func, and it has one template parameter, type t. And after that, I declare a class demo. And then in main, I call func with demo passed as a parameter. If you look at this in C++ Insights, and if I do transform this, then we can see here the resulting generated template instantiation of func for demo. Here I have my class demo. And that's the reason why this code would not compile. That's the reason why it's guarded by this ifdef insights use template. So you can define it if you like to see what's going on, but per default, it's disabled. And the reason is when this template instantiation is parsed by the compiler after this transformation, there is no class demo, there is no type demo in the type system, because demo is declared afterwards. Okay, so without this ifdef guard, that code would not compile. I can, of course, by hand, move that class demo around, put it before the function, and then it would compile. The reason is that I'm really easy on generating this template instantiation. They are inserted directly after the primary template. And that may be the wrong point. So one possibility would be trying to figure out where is the right place to place it. I haven't checked that deeply. There are other things, so you cannot have a template specialization in a class. So I have had to move things out, and I haven't done this yet. So it's just instantiating at the point where the primary template is declared. The project itself, it's still under active development, so not all statements are transformed yet. There is a pull request, or not a pull request, unfortunately not, an issue open for supporting C++ 20's coroutines. If you have insights or experience with that, I'm happy if you can share them. Now I said that C++ Insights uses the abstract syntax tree of the compiler, and I like to give you a feeling what that is. That's part of an AST of a C++ program. And it's only the last fragment, maybe 1% of the whole AST flooding over my screen when I'm dumping this AST. And the reason for that is that this program uses parts of the standard library, and that involves a lot of template instantiations and other things created in the background, so the AST output is very large. If you submit an issue report for C++ Insights, I'm very happy if you can avoid using the standard library. Not because I dislike it, but it makes it really hard to see through all that things. What's the C++ code behind this AST? What's roughly the program that this AST models? Sorry? Yes. It's a main saying cout hello C++. So over the time I grew to being more fluently in reading the AST output. One word about this talk as we progress. It's a bit special because I today try to reach two parties. One are teachers, because one aspect of creating C++ Insights was for teaching and still is for teaching. So I will show you some examples in C++ which I'm really sure that you're already familiar with. So you know what they are doing and so on. The purpose of that is just to give you some glimpse into what is C++ Insights able to show you with things you already know. The other part is to address a little bit the interest of experts. So I have some C++ 17, some C++ 20 things in there, which I assume not everybody is already familiar with. Starting with something more or less trivial, I stumbled over this during the development because it worked just out of the box when I implemented something. And that's default arguments. I believe everybody knows what default arguments do. In this case, I have this function here, func, which has one parameter x, and it has a default argument 23. So whenever I call func without an argument, x is 23. But how does this work? I mean, for us, it's easy as programmers, as developers. For the compiler, I never questioned that. It's just syntactic sugar. Saying, hey, you gave me a function with a default argument. That value is 23. Whenever I approach a function of that type without an argument, I put in there 23 as a parameter. So functions with default arguments are not so special, at least if you're not a compiler implementer. In C++ today, we have a lot of different ways to initialize an object or type. There is an entire 1 or 1.5 hour talk by Timo Dumler just explaining the different ways of initializing something in C++. It's an excellent talk. If you haven't seen it or heard about it, go check it out on YouTube. He gave it, I think, at Meeting C++ last year and at CPP on C this year. I'm not talking the rest of this talk about initialization. It's just a small part. Here I have an example of 4 char arrays of size 5 and 4 different ways initializing them. The first one we had all the time. It's an uninitialized array, doing nothing. It's always nice that we can have the things. It's performance critical and we know what we are doing. I prefer not to have uninitialized variables. Anyway, the second uses C++11's praised initialization, requesting a 0 or default initialization. Now, when teaching that even to experienced C++ 98 programmers, some of them say, well, I like to see the value that thing is initialized with, so I prefer version number 3, stating explicitly I'm initializing this with 0. I don't know if that ever happened to you or if you ever saw something in a code review. And there's another party saying, well, we are not initializing things to 0. We chose 77. So that's way number 4. Let's have a look. If I transform this, then of course we see A does nothing. It's uninitialized. 2 initializes all elements of that array with 0 or an equivalent to 0 because we are talking about a jar here. That's nice. I do not need to know the size. I don't know how often I had to type a memset in the past to initialize in such things. So it's really nice to be able to just put in there empty curly braces. Then version number 3 looks a little bit different because the first 0 is different than the others. They all result to be 0, but the first one we can see is the integer 0 we put in there to initialize what some people think the whole array with. But here we can see only the first element is initialized with this 0 and the rest is filled with the 0 or default initialization of that type. And that's the reason why, of course, number 4 does not turn out how it's supposed to be, because as soon as we specify a value, we initialize only that element, the first element of that array. So it's not hard if you think about it, because how would you otherwise initialize an array with values? But it sometimes confuses people, and that had helped me in the past to show and prove to them why it is different. Yes?
Remind me, does the fact that you're using the curly brace there prohibit narrowing conversions on all of the elements? In other words, there are contexts in which the curly brace initialization prohibits a narrowing conversion. So what I'm wondering is, had you put a value, 77 there still fits in the character. Had you put a value there that was larger, would it then reject it? If you put in 50,000 as the value.
So okay, the question is, do the curly braces also prohibit the narrowing conversions, which they usually do? And what's happening if I'm putting a larger value there? Then the answer is it will fail. So because it's in this early stage of the front end, I only can transform compiling code in C++ inside. So I don't know whether the question was about language or about a tool. The language will not allow it, and the compiler will fail early, so I cannot do a transformation, and it shows the right thing. It does nothing.
Yeah, in this case, though, you're not at the point where you can identify why it failed. In other words, you simply see that it failed, and the reason for that failure is that's something you don't display.
Yeah, to be fair, that the compiler gives you a warning about that. Yeah, I also print out the compiler warnings, so it's the same thing you would get if you just compile this example with GCC or Clang. And I'm also not sure if I would be able to transform this, what should I show there? The error message as a comment? Okay. Okay, so, all right. Okay, you couldn't see that. Perfect. Another thing, because I teach a lot of classes to people who would like to learn C++ 11, 14, 17, we got this new feature in class member initialization. And I have here another small example, a class called init, which has a default constructor and 3 members. One int, a std vector of int, and a std string. In my default constructor, I'm initializing the int member I to 9. And then I'm using in-class member initialization later to initialize all the 3 members to some values I like. 0, 1, 2, 3, and hello. And if I do transform this, then we can see what magic happens here. It's once again just syntactic sugar the compiler does for us. So the inline initialization values we provided, the compiler just moves into the default constructor and it's initializing the std vector with 1, 2, 3 and my std string with hello. So what's happening there is nothing special. It's the code we can write ourselves, but so we cannot forget it. And one question sometimes comes up is, what happens to I? How often is I initialized? And the answer is just once. Either with the value I provided in the default constructor or in any other constructor, if you're looking at other constructors, in my case 9. And if I would totally skip providing that value, then the default would take place and it's 0. So there is no double initialization or things like that. It's either the value I provided as a default or the specific value I provide in a constructor. And that's one of the parts where I experienced that it helps that people can play around with these things. They can fill in values, they can take off values, and they see how it results in their output. Another big thing in C++ these days are Lambdas. So here I have an example I showed in my talk yesterday already. I have a const char array named hello with the string hello and the C TechTown in it. And then I have a lambda which captures by reference that string and prints it out in a printf. Let's have a look what the compiler generates for us for this lambda. What is a lambda in C++? We can see some side effect of C++ inside. It tells you the size of the array because it's known at this moment, so even if you haven't specified it at the right, at the left. Then our lambda is in fact a class. The closure type of a lambda is a class. And the compiler generates this class for us, and it takes care of all the captures, because the captures become members in that class. That's why I have here an const char array of references of size 19 to capture the char string from outside. Next to that, I have this member function, which is a call operator. And this call operator contains the body I wrote for the lambda here. So it's just moved to here, into the call operator. And this call operator is then called or invoked later when I invoke the lambda. If I change my capture by reference, for example, to capture by copy, then we can see that now I have a char array, a const char array of size 19 and no longer an array of references. And if I say now that this lambda should be able to alter that captured string. If a close look on the call operator, if I'm saying that that thing is mutable, the const specifier of the call operator goes away. So that's how things work there. I really like it because it uses facilities already available in the language, and just with some syntactic sugar and probably a lot of implementation effort on the compiler side, we can use these nice things and create existing code.
Question.
Sure?
I noticed you commented out const expert.
Yes.
The inline there. Can you elaborate a little bit on what's going on there?
Sure. Remind me to not do it twice because I have a slide later, but it's an excellent point here as well. With C++ 17, we got implicitly const expr lambdas as a language feature. And that means that, at least from my understanding, in the Clang implementation, whenever they see a call operator in C++ 17 mode while parsing your C++ code, they add const expr to it, because it can be const expr. And later on, after processing or after having generated the AST, doing the real compile stuff, they're evaluating the body of the call operator, checking whether or not it satisfies the requirements of const expr. If it turns out that yes, it satisfies the requirements of const expr stays. If it turns out that no, there is something not allowed in there for const expr, they just take away the const expr specifier and evaluate the function at compile time. Because it makes no sense to promote that to the user because we didn't explicitly specify that it should be const expr. So they have the liberty to do it either way. And that's why at this stage, I cannot tell you reliably whether that thing is const expr or not. What you will see there, if I switch back from C++ 20 to, let's say, C++ 14 mode, the const expr is gone because the compiler no longer inserts it. So I try to show only the things the AST gives me. I have to sketch some things up, for example, the name of the lambda. Compiler does not need to generate one for it internally, so I make one up. But in general, I try to stick really close to the AST. And that's why it is in const expr. To give you a clue, it can be const expr, but sorry, I cannot tell you for sure that it is. I haven't found a way maybe to trigger the evaluation machinery to get the result early. Another small example. I have this main function here, and it creates a variable named collection out of a type which seems to be a class template x instantiated with int. And then I have 3 different for loops, range-based for loops, which iterate over that collection. This code compiles. My question to you is, which of these 3 range-based for loops are correct in the sense that they are doing what they are supposed to do? Just give me a number from 0 to 3. You're saying 2. Do you have any other number than 2? One. 2 is the correct answer. Let's have a look at this. So the first range-based for loop says that the range initializer is of type const x, const int. And this is not the type we used before when we declared collection. So this is obviously wrong. The second one, on the other hand, uses const x int. That's exactly the type as we given it before when we declared collection. So that one is correct. And then we have the third version which uses auto, and of course auto does the right thing. So For loop number 2 and 3 are correct. 1 is the odd one. Do we all agree? Well, boy, you should have asked me for the documentation about that thing. So this is the code. And if I scroll down here, then at the bottom I will find my range-based for loops. So first I have the declaration of my variable collection, and then we can see here this opening and closing scope. That's a range-based for loop. Range-based for loops generate a new scope for us, and in that they declare a range variable begin and end. And then they use a regular for to check whether we already reached the end, and if not, of course, the body is called, and then they use the pre-increment operator to increment begin, which takes a lot of performance issues from us. This is our variable x, which we requested in the range-based for loop. And it's initialized with calling begin, and for that, the dereference operator. Looks good, doesn't it? Let's have a look at range-based for loop number 2. It's the same, except that for the initialization, we get here what appears to be a constructor call. So it's still begin one dot operator star. So it's still begin dereferenced, but then there's a constructor happening, creating that object for us. Let's have a look at the auto case. Auto does it the same way as our first range-based for loop, which appeared so odd, because we specified that x is of different type because of the const than how we initially declared collection. And why is that? It's because of that. Because the iterator which is returned from x is of type x const, whatever type you passed in first. So the iterator which is returned for that range-based for loop from that type x is not the original type x, it's a const version of that original type regarding template parameter. And why I'm telling you this? Who knows stud map? Yeah. The key of stud map is const. However, when we are creating a stud map, we are saying something like int, comma, stud string. If we are iterating over a stud map, then this is exactly the trap we can run into. Because what's returned there has a constant key. So the first element becomes const. And that's why some of us advise that you should always prefer const here, because it does the right thing by default. Or ask and look at the documentation. While we're talking about range-based for loops, I really like them and I'm super happy about them and try to apply them wherever I can. And some things that make me sad are things like that. Here I have an example where I have a stud vector and I'd like to iterate over that vector and print the elements out. But together with that, I like to print the index at which that element is in the vector. And doing that, I need some helper variable, idx, to have the index counted and incremented. And that variable idx now is outside of the range-based for loop. And with that, it's leaking in the adjacent scope, and it isn't so beautiful anymore. It's one thing about a range-based for loops, that everything is tightly together, and for that case, I have to do something different. Well, I can use a stud algorithm, for example, for each, pass in a lambda doing that thing, but then still, that idx variable has to be somewhere. So, same pain. At least if you like to see the code like me. The good message is, In C++20, we will have range-based for loops with initializers, which enables me to write code like this. I now can say for paren open size t idx semicolon and then the rest of the former range-based for loop. And with that, it's again tightly coupled. If you look at what's happening there in C++ inside, it's again surprisingly easy. Here we have the opening scope of the range-based for loop. And after that, our variable is declared. So it's only visible in that scope and will be destroyed later. Yes?
Can you have an arbitrary number of initializing?
So the question is, can I have an arbitrary number of initializations like this?
Yeah, not the different types. So we have several semicolons.
That was not possible before, and the language rules didn't change there. So it's not what you're. So the question is, if I get it right, can I say something like this? Is that right? Yeah. And to my knowledge, that wasn't possible ever before in a usual for loop. The compiler says that with this comma separation, there is only one declaration allowed. So that the first type has to be. You cannot have. Ah, you're asking about multiple semicolons. I didn't get that. No, you cannot have that. So it's, once again, a little syntactic sugar. And if I took it right from the notes, it was already not that trivial for some compiler vendors to implement it. So that's what we are having. So it's just a single type. So suggestion is you can use a tuple to hack around it, or std variant, or whatever you're needing. I lied a little bit to you before, because there is a way to get what I like without C++20's range-based for loops with initializers. I can use, for example, my std for each algorithm and use C++14's init capture to introduce a new variable called idx in that lambda, which is of size t and default initialized. So it's how we can put the pieces together. That's C++14's Lambdas extension. In C++17, we got a little extension to Variadic templates. We can now apply parameter packs together with using. And what this does is enables us to have in line number 4 this using ts call operator ... thing. Well, we're looking at a Variadic class template which takes an arbitrary number of types and derives from each of them. And this using statement says that from each of these types, please drag in the call operators, all we have, into the overload struct so that they are accessible. Nico had an excellent example how to apply that in a bigger context yesterday in his talk. If you've been there, and if not, just check out a video. What this thing does now is I can use this together with a deduction guide, which you can see in line 7 to 9, and use it in line 13 to create a struct which contains multiple lambdas, if you like, or it derives more precisely from multiple lambdas, in my case 2. One that takes an int by reference and the second one that takes a double by reference. The first one multiplies the passed value by 2, the second one by 2.0, and it has also a second variable which is multiplied by 2 again. And now I can use this created type double DBL to either call it with 1 parameter in line 21 or with 2 in line 22. Looking at what's going on there, we can now see another template instantiation. Here, our class overload gets instantiated with two different lambdas, the two ones I created. They used to derive from them publicly. And this is the part where my using with the operator ... comes in. Now I have a using declaration for both operators of both lambdas. The operators of both lambdas. Because it might help, C++ Insights gives you here as a comment the full signature of the call operator you got from the type. So from the first lambda and for the second one, which can help you to figure out why things go not as expected, probably. And then down here, we can see, of course, the lambda as we've seen it before. And then here, our overload is created with the two lambdas. And while I prepared this talk, I discovered something I didn't expect, and I have no answer to so far. Here's the first call, calling that created object DBL with just a single argument. It's an int. There, the call operator on double is called. While in the line below, for, to me, so far unknown reason, this DBL variable is casted to the type of the lambda. So the compiler at this point seems to know better what to do. And then it invokes the call operator. I'm not sure if it's more efficient to do it that way. I was just surprised. Yes?
Wouldn't you skip the virtual function resolution this way? If they were virtual.
So the question is if that thing would skip the virtual function dispatching, if there was or were a virtual function. And that's what I thought too, yes. It's just because there is no virtual function, I'm not sure if there's more going on I'm not seeing. So maybe it doesn't need to figure out an address offset, or I don't know. For the virtual part, I would be totally in. I think that's what make it fast. And maybe that's a general optimization they are doing. And if it doesn't matter, it doesn't matter. It does not make things worse. So maybe that's the idea here. So what else do we have? We have in C++ 17 a constExpr_if. And you may have heard of that. The goal here is that only one of these if branches survives after parsing it, because it's constExpr. All the others are discarded. But all branches have to be valid. That's one rule. And if we, once again, like to verify that, here's a bit more of the code, but it's just to make it compile. Then we can see below here, I have the primary template, which contains all the branches. And then I have my template specialization, which only contains the Linux branch, because I stated that my native OS currently is Linux. So all the other branches go away. But I'm lying, I'm on a Mac. So if I change this, then I'm getting an error. But, well, who likes static asserts, right? So it's right away. Now what we can see here is the first the Linux branch is empty. It's there, but it's empty, so it doesn't bother the compiler. And then we have here now the Mac branch surviving. Yes?
You're missing the context on the line 34.
Yes, thank you. That's where I'm getting. So if we are looking closely at this code, we can see something I didn't bother with for years with C++ and C. And the key here is there is no else if in C++. There's an if and there's an else, but there's no else if. There are languages like Python, Bash, they have a else-if keyword. In C++, we just have a else and a if. And that's why I have here a const expr if and a const expr else branch. And notice that here opens a new scope, and in that scope is my if, because that's how in C++ and C a else if is modeled. It's just an if inside a else. And that's why this marked else if is not const expr. It's a regular if with an else branch within a const expr else. And if I add const expr to that, I can put in the static assert. You should not comment out a static assert like I just did. And then we can see now I have only that if branch that survives. There is no else branch anymore. And that's important to know, because if you're not having a static assert there and not doing a lot of checks, it may slip under the radar. So remember to put on every if a const expr if you like to have a const expr if, even if it's together with the else. That's the takeaway here. Yeah?
This always false, is that part of the standard library? Is that something you...
No, that's something I created that comes from another fact that if I would use a plain stood as same or something like this here, or the static assert with a always true, then it would always trigger because the branch is always evaluated. And if I'm putting here, for example, the typical other problem, the static assert is essentially always true. I should never reach that. And it's a const expr if, so you might think, sorry, I should say it's always false, not always true. And now it stops compiling because that branch is evaluated, and as soon as we hit that static assert, it triggers. And that's why I have this, this always false template around it. But it's not part of the standard library, I think, yet. I have my own implementation.
It's because the static assert now actually depends.
Yes, because now the static assert depends on the template parameter, and that's why it is discarded later and not triggers. Yeah. So with C++ 17, we got other nice tools. We can now use auto together as a non-type template parameter, which enables me to write code like this. I have this print function, which is a template. And I can now say here that the first parameter is of type auto, and name it sep for separator, and it's default initialized with the space. And after that, another template parameter comes, and then there comes an arbitrary number of template parameters because it's a Variadic template. And now I can use this first argument, this auto non-type template parameter, to use it as a separator to insert between each of the arguments this separator. And that I can then use to print out hello C++ 20. Nice and easy. If I look at this, C++ Insights, we can see what's happening there. Compiler creates a bunch of template instantiations for us. First, we have a print version with all of the elements or all of the arguments passed in because it's a const expr if. I have this terminating case here. Then there's a version where one argument is popped, and there's the last version where only one argument remains. And that's how I terminate this recursion. So here I have a recursion. But that's one way how you can apply this const expr if. But C++ 17 gave us something more. We got fault expressions there. So I can change this example slightly, applying lambdas, another liked feature, together with fault expressions to achieve the same thing. And if I now transform this again, then we can see, first of all, I only get one instantiation for print because I have no recursion anymore. And that has all the parameters, of course. It creates a lambda, which contains my cout here. And what we are looking here at is a generic lambda, which we got with C++14. And now we can see that that generic lambda, this auto keyword we can apply here, results in our call operator in the lambda being just a template. And my auto parameter is now a template parameter, or template argument, depending on when you're looking at it. And that's why I'm getting in this lambda two more instantiation, one taking a reference to a const char array, and another one taking a const reference to an int, because that's how I call the lambda. And then below here, we can see what default expression does. It just comma separate the calls to the lambda's call operator. Once again, syntactic sugar, just to enable us to write less code and better code. Okay, we already talked about const expl lambdas, so we can skip this. If you like the project, you can support a project. My favorite support number one is go to GitHub, pick an issue, and give me a pull request. Also very favorable is if you find a bug, file an issue. I also like that. Also great support. If you're more on the, hey, I have a lot of money to give you side, aside from hiring me for training classes, you can support me at Patreon with small amounts of memory and the project with that. If you like to be more on the side, I like to show, then maybe Spreadshirt t-shirts with the C++ Insights logo are the right thing for you. All that helps to fund the servers and all the stuff that thing runs on. Some time ago, when I tweeted about a new feature, I got this tweet back, which seems to come from somebody which is able to speak English and German. And the question was, so it's completely Fertig? And the answer is no, I don't think so. It's the start of the journey. There are a lot of C++20 things to implement. I guess not all things are already implemented, and there are most likely some issues. So it's a good point, but it's not the end. With all that said, it's been a pleasure giving the talk to you today. I have just 3 more words for you, and that's I am fertig.